Dear civil engineering and water resource student, this is Biswajit Majumdar, and in this class I am going to talk about and define you the fundamentals and practical application of the civil engineering or water resource engineering or environmental engineering course, which is open channel hydraulics or open channel flow. As you can see, there are mostly two types of flow. First one is, let's take a look at the pipe and how it is different from open channel flow. We will know that in this section. Now imagine a pipe like this. Now there is a certain flow inside the pipe. Now the flow is flowing and the pressure subjected to the flow, which is acting on a closed volume, which is a cross section of the pipe, which is a closed volume. So in this pipe flow, if I dig a hole at this place I dig a hole, if the pressure inside the pipe is greater than the atmospheric pressure, then what happens? The water will rise, say up to a certain height h, the water will rise. Now from this thing we can say the pressure here is a function of height. This thing. The pressure is here subjected to a closed surface in pipe flow, and the height is a function of height of the flowing water. If we dig a hole at the pipe, is a function of the pressure. The pressure is a function of that height. Now in open channel flow, what happens? In an open channel flow, say this is a river, the water surface of a river. This is a water surface of a river. Now draw it. Now in this water surface, this is mostly a free surface flow. You can see this is a free surface flow. Now in this flow, the pressure subjected to the water surface is nothing but the atmospheric pressure. So as you can see in the pipe flow, there the pressure subjected to the flow is due to the closed surface, and here only atmospheric pressure is subjected to the open channel flow. In that case, in the pipe flow, if we install a pump here, say a pump here, then we can navigate the flow so that it can happen from a lower pressure to a higher pressure, isn't it? But in open channel flow, if we consider two sections, 1 and 2, the energy, the pressure, both will be higher than the value of this section. So in open channel flow, water flows only from higher pressure to lower pressure, higher energy to lower energy. That's the fundamental difference of how we can differentiate a pipe flow and a open channel flow. Like as you can see, this is a trapezoidal channel. This is a circular channel. If the flow is something like this, the cross section of the flow is certain like this. I mean, this is the weighted value. Then this is a semicircular. This is a trapezoidal channel. And this is a proper rectangular channel. Now, here is, I want you to know a very important parameter that can define the property of the flow, which is, that can be denoted by HD, which is the hydraulic depth, which is A by the top width, where A is the weighted perimeter area or the top area, and the B is the width here. Now, if there is a open channel flow like this, now there are several physical and mathematical significance of the flow. In mathematical part, there are three things which generally coming out, which is mass, energy, momentum. Now, the conservation of the mass, energy and momentum, these are the things that can help us in the mathematical derivation of any open channel flow, exist in nature or artificial. Now, the conservation of mass, which is called the quantity equation, this is head or total head, you can say. I will explain this later. And this momentum, we will understand this by the most beautiful natural phenomena of our environment, which is hydraulic jump. Now, these are the mathematical and physical significance of open channel flow. Now, we can classify it based on the flow property, this thing, mostly few ways, which are steady flow. Now, what is a steady flow? If the rate of change of discharge according to time or according to a distance equal to 0, then this is become steady flow. Then what is unsteady? The same thing, where the change of discharge respect to time becomes non-zero or respect to distance, whatever. And there is another parameter which is uniform flow. If the flow depth doesn't change with respect to time or distance, then this is called uniform flow. And in the non-uniform flow, easily you can derive when this thing changes with time or distance, then it will be non-zero. Okay? So, we will understand all these things more deeply in our next derivation part, where we will derive the continuity equation for any open channel flow, derive their energy distribution system, so that will help you. There is a open channel flow. This is the atmospheric pressure. Now, if we derive or think of two sections between the channel, okay, there are two sections between, like this is the dx, and we imagine the cross section of the channel, or that's between the section, so that thing becomes our H if the flow depth is this. Okay, that thing becomes our cross sectional area, the total area of the cross sectional area of the channel, or the change of the channel with respect to time or distance. That thing becomes our dA, and this is become our top width. Now in that case, the conservation of mass equation, the equation of conservation of mass or the continuity equation, what it says generally, it says that the flow entering into section 1 is the same flow leaving from section 2. Or we can say the volume of the flow entering through that section is the same flow leaving from that section. Now define that flow. So in that section, if the discharge is Q, then the mass flow is Q into dt. The volume of the flow. From the section 2, the same thing is Q plus del Q del X into dx into d. If you ask me about this term, this is nothing but, imagine if the discharge is changing with respect to the distance, then the partial change of the partial differentiation of the discharge with respect to x becomes del q del x, isn't it? Now if the del x become 1, okay, for a unit del x, this thing, the change of partial change of discharge is this. So if the length is dx, so what will be the total change? This. Now in that part we can get the change of the volume, which is nothing but Q plus Q into del T, sorry, which will happen Q dt minus, this is for section 1, this is for section 2, Q plus del Q del T del Q del X into dx into dt. So that thing came out as, this thing cancel out each other, minus del Q del X into dx into dt. Remember this part? I will erase the remaining part of the equation.